All right, folks, welcome to the Morrison Planetarium. My name is Cheryl, and I have the pleasure of being your pilot today through a tour of the universe. And I'm not just a bodiless voice coming out of the walls, I'm a real person, and I am right behind you in the control booth. Hello, welcome. Nice to see some faces. Glad to have you here. So this show is a little different than the ones we have throughout our day here because this show is 100% live. I'll be flying us away from our home on Earth to explore our solar system, our galaxy, and go out to the visible reaches of the universe. Now, our spacecraft today is a software called OpenSpace that was built in partnership with NASA and uses models to create a 3D visual of our universe. It also uses updated information, so everything that we see today is almost in real time out there in space. And the software is also open source, so you can download it for free onto your gaming computer at home to explore the universe at your leisure. And if you want to learn more about that, you can find me at the end of the show. Now, before we get started on this tour, I do have some housekeeping items to review with everyone first. So first of all, I do highly encourage folks to wear a mask in this crowded indoor space. And in an effort to keep the space clean for you and future guests, we do not allow any eating or drinking in here. Now, if you'll have any electronics on you today, like your smartwatches, phones, cameras, etc., please take a moment to either silence them or turn them off and tuck them away. We do not allow for photography or recording during our shows. Also, during the shows, this dome gets very dark, so if you're standing or walking around, it can be easy to stumble or trip. So for your safety, I ask that you stay seated. But if anyone needs to leave early, you can use the exits at the top of the planetarium going up the stairs on both sides. And finally, thanks to our very large dome here, our shows get pretty immersive. So if you start to feel any discomfort like motion sensitivity or dizziness, please take a moment to close your eyes and take a few deep breaths. And that should give your brain a chance to remember you're comfortably sitting in a planetarium and not actually hurtling through space. All right, now without further ado, let's get started on this tour. So we're going to begin our journey a few hundred miles above the Earth here at the International Space Station, or the ISS. Now this is essentially a large orbiting research station that slowly gets larger as more modules are added to this structure. It is the largest object that we have built and put up into space so far. Its size is comparable to an American football field. And also lengthwise, it's actually about the size of our academy building that we're in right now. Now, nations around the world participating in the ISS program will send astronauts to live on the ISS, where they will work through experiments to learn how things like water, fire, plants, and even how our human bodies function under the harsh conditions of space. Nowadays, the ISS is the farthest that humans travel into space. And at any one time, we can comfortably fit 6 astronauts on the structure. Now, the ISS actually orbits the Earth 16 times every day. So it's moving pretty fast above us. And you can actually find out when the ISS passes over your area by checking online at spotthestation.nasa.gov. If you're looking for it on a clear night sky, it'll look kind of like a bright little star that's moving very quickly in a very straight line through the sky. Now, as we get farther and farther away from the ISS and our planet here, we are going to see how far our human influence has spread throughout space, how far humans have physically traveled, how far our spacecrafts have gone, and how far our human communications have gone as well. And next, we're actually going to stop by Earth's moon, the 5th largest moon in the entire solar system, which is pretty impressive since there are over 200 moons in our solar system. So let's fly on over there right now. All right, now it looks like we're coming up on a pretty crescent moon here. And while that is beautiful, I do want to make sure we all get a nice clear view, so I'm going to turn the light on. Now the moon is Earth's closest natural neighbor. And for millennia, our moon has been important to humans, helping us track time and inspiring myths and legends of different cultures. Every 28 days, or about a month, the moon completes a full orbit around us. But we only ever see one side of the moon because it revolves around us and rotates on its axis at the same rate. I'm going to fly in a little bit closer here so we can see all of the impact craters on the moon's surface. Now, many of these craters are named after different scientists and astronomers like Tycho, Marie Curie, and Tereshkova. And it may look like the moon has been hit by asteroids and meteorites more often than us, but Earth is a much bigger target, and we have had our fair share of impacts. But because the moon doesn't have an atmosphere like Earth, nor does it have any wind, water, erosion, or even tectonic plates, there's nothing to erase these craters after they appear on the moon. And most of these craters are also very old. One of the more recent craters was formed over 100 million years ago, so a bit while back. And the moon is as far as humans have ever traveled out into space. NASA astronauts Buzz Aldrin and Neil Armstrong were the first humans to walk on the moon's surface in 1969, and since then, 10 other NASA astronauts have walked on its surface. But currently, NASA is planning a new mission to the moon called Artemis, where they will send the first woman to the moon and lay the foundation for humans to start planning our missions to Mars. Now, our moon may be our closest natural neighbor, like I said. It only takes about 3 days to fly up there, but it's still a whopping 250,000 miles away from us. And as we continue on this tour, distances are going to hike up into the millions, billions, and even trillions. And at that point, it doesn't really make sense to use miles or kilometers as a measurement of distance anymore. So instead, we're going to talk about distance using the speed of light. Now, the visible light that we see is part of the electromagnetic spectrum, and it is the fastest thing in our universe that we know of, clocking in at almost 200,000 miles per second. So if NASA astronauts were traveling to the moon at light speed, instead of taking 3 days to get there, it will only take them 1.5 seconds. So we say the moon is about 1.5 light seconds away from our planet. Now, light speed is also a measurement of time, but let's talk more about that at our next stop. We're going to fly over to our sun. There we are. Okay. Now, the sun is 8.5 light minutes away from the Earth. That means when we look at the sun from Earth, we are seeing what it looked like 8.5 minutes in the past, because it took 8.5 minutes for that light to leave the sun, move through space, and reach us here on Earth. Now, our sun here is a middle-aged dwarf star, about 4.5 billion years old. It's mainly composed of hydrogen and helium, and its massive gravity holds our entire solar system together. And just like the Earth, the sun also spins on an axis. But because it's not solid, the sun's made of gas, different sections will spin at different speeds. For example, the sun spins faster at its equator and slower at the north and south poles. And obviously, we don't send humans to the sun. But in 2018, NASA launched the Parker Solar Probe to learn about our sun from up close. And recently, Parker Solar Probe entered the sun's solar atmosphere closer than any spacecraft has come to our sun, where it was able to sample particles and the magnetic field there. And so spending time learning about our sun can really help us better understand our own planet Earth and other stars in the universe. Okay, now you can go ahead and stow away your sunglasses. We're going to head out to the other planets in our solar system. Now, first, we're going to start to see our rocky inner planets, Mercury, Venus, Earth, and Mars. And then further out, we're going to start to see the orbits of our gas giants, Jupiter and Saturn. At the very edges, we have our icy giants, Uranus and Neptune. Now here, you may notice that there's a pretty sizable gap between Mars and Jupiter's orbits. But this isn't just empty space. This is where we find most of the asteroids in our solar system. This is where we find the main asteroid belt. And back in 2015, NASA used a spacecraft called Dawn to explore a particularly unique body within this crowded asteroid belt, a dwarf planet named Ceres. Now, here is that dwarf planet's orbit around our sun. And not a lot of people have heard of Ceres, but there is another dwarf planet in our solar system that is very popular, very well known. Does anyone know the name of that other dwarf planet? You can shout it out if you know it. Yes, Pluto, the dwarf planet that is out past Neptune. Now, Ceres and Pluto have pretty similar stories to each other. When we first found Ceres over 300 years ago, we thought it was the only thing orbiting in between Mars and Jupiter. But around that same time, a lot of astronomers are starting to find a lot of small rocky objects that they were calling asteroids. So Ceres was changed from a planet to an asteroid. And similarly, when we first found Pluto, we thought it was the only object orbiting out here. But then in the late 90s and early 2000s, astronomers started to find all these other objects. They found the Kuiper Belt. Now, these are mostly small icy objects, but some of which are around the size of Pluto, and at least one is almost as big as Pluto. So instead of adding another dozen or so planets for all of us to memorize in school, astronomers around the world, they got together and created a better category for these small objects, dwarf planets. And so now there are 3 requirements for anything to be a fully fledged planet in our universe. 1, it needs to orbit a star. 2, it needs to be large enough or massive enough that its own self-gravity can pull it into a round sphere shape. And 3, it needs to have cleared its orbit. Now, Pluto, as we can see here, goes right through the Kuiper Belt and doesn't have a clean orbit. So as of 2006, we don't call it a planet anymore. But Pluto does still orbit the sun, and it is big enough to be a sphere, so it's a dwarf planet, shifting from the smallest of the planets to now the largest dwarf planet in our solar system. And today actually marks the anniversary of the day Pluto got demoted to a dwarf planet. It's been 16 years, y'all. Now, while we can still see Pluto, let's use its orbit to help us get a sense of distance. At light speed, to get from one side of Pluto's orbit to the other would take us about 10 hours. So that is 10 light hours across. Now we know that humans haven't traveled to any of the other planets in our solar system yet, but we have sent robots like rovers, probes, and other unmanned spacecraft to explore for us. So these orange lines here are showing us how far our fastest and farthest spacecraft have gone so far. They were all traveling fast enough to escape the sun's gravity and leave the solar system. We have Voyager 1 and 2 and Pioneers 10 and 11, all of which were launched in the 1970s. And most recently, we have the New Horizons spacecraft, which went out to Pluto in 2015. That short orange line you see that intersects Pluto's orbit, that is New Horizons. And all of these spacecraft have traveled pretty fast and definitely journeyed far. But even still, they have only gone as far as light can travel in one day. So they have a ways to go, and so do we. So let's keep flying. Because now I want to fly us out to interstellar space so that I can show you the very farthest that our human technology has reached out in the universe. So let's do a little bit of flying here. All right, we are far enough, so now we can see our radiosphere. Now, this radiosphere, it represents how far radio waves emitted from Earth's radio and TV signals have traveled since we first broadcast them. Now, radio signals that were strong enough to escape our planet were first sent out in the 1930s. So this radiosphere is about 90 light years away from us in all directions. And remember, radio waves travel at the speed of light. So this radiosphere gets 1 light year wider every single year. And while we're out here, I also want to show you the other planets that astronomers have identified. Now, every one of these markers is a star with at least one exoplanet around it. That's a planet outside of our solar system. And we have found thousands of weird and interesting exoplanets so far. And just this year, we were able to confirm over 5,000 exoplanets, which is incredible. And astronomers use telescopes like the James Webb Space Telescope that was launched in December of last year to explore these exoplanets using infrared technology. And now, if you look carefully, you can see that there are actually several exoplanets inside of our radiosphere. So if there is life on any of those exoplanets, they would be able to detect our old radio or TV broadcasts, which would be pretty incredible. But let's keep going, because we are still only flying past stars in our galaxy, and we haven't even gone outside of our Milky Way yet. But as we zoom out, I do want you to keep an eye on our radiosphere and see how long you can keep track of it. Soon, we'll start to see the large-scale structure of our galaxy. We live in a spiral galaxy, so it's pretty flat, like a disk. And it has spiral arms of gas, dust, and stars. And we are in one of those spiral arms, about 2/3 out from the center, in an arm called the Orion arm. And right at the very center here, you're going to see this bright group of stars. So it's really densely clustered together. And if you could see past all of those stars, right to the very, very center of the Milky Way, you would see, well, basically nothing. Because we have a supermassive black hole that is at the center of our galaxy. It's called Sagittarius A star, and it's about 4 million times the mass of our sun, so pretty big. And actually, this year, astronomers were able to capture an image of this supermassive black hole, which is pretty incredible. So you can find that online. All right, I'm going to stop flying, give you a chance to spot our radiosphere before I point it out. It's pretty small. There's a tiny, tiny dot right there. That is the farthest that any of our human communications have gone out into space so far. And now we're up to distances of thousands of light years. From one side of the disk to the other, our galaxy is about 100,000 light years across. But our galaxy, with its roughly 400 billion stars, is just one galaxy out here in the universe. Every dot that we are seeing now is not a star, but another galaxy with its own billions or sometimes trillions of stars. Now, the closest large galaxy to our Milky Way is the Andromeda Galaxy, 2 million light years away. But don't worry, it's slowly moving closer to us each day, and it's going to get here in about 5 billion years or so. Now, as you see here, galaxies are not evenly spaced out. They tend to cluster. The Milky Way and Andromeda galaxies are grouped with about 40 other galaxies in a cluster called the local group, kind of like our galactic neighborhood here. And astronomers use the different colors that we're seeing here to show the different galaxy clusters and help identify them. Now, if we fly out far enough here, we're going to start to see a kind of strange shape that these galaxies seem to form. It's kind of like a butterfly or a bow tie. Now, the universe is not actually shaped like this, but it looks like this because we're looking out at the universe from our perspective here on Earth. So this is a map of the galaxies that we can see and have found so far. And since this is all from our perspective, it does make a few things look a little bit strange. For one thing, it makes it look like the Milky Way is right at the center of everything here. But as far as we know, there is no center to our universe. If you were to go to any of these other galaxies, it would also look like you're right at the center with everything else moving away from you. And the other strange things we have here is this very large gap up here and this even bigger gap we have down here. Now we see these strange gaps that kind of create this butterfly shape. We see them because the flat disk of our own galaxy, which has a lot of gas, dust, and stars, is actually obstructing some of our view of the universe around us. So there are even more galaxies to see and map in those directions. And over time, as we innovate our technology, we will begin to fill in those gaps. But if we go a little bit farther here, we're going to start to see some of the earliest objects in our universe. Quasars, highly luminous cores of some of the first galaxies formed in the universe. One of the largest known quasars is named Ponua, a colossal object powered by a supermassive black hole that's 1.5 billion times the mass of our sun. This ancient quasar was formed over 13 billion years ago. And when we use our telescopes to view quasars or anything out in space, we're kind of time traveling, because the light from these objects has to travel so far across space that by the time that light travels all that distance and gets into our telescopes, we are seeing the light of these objects as they were in the past, not how they look today. So this was the same point I made earlier about our sun. When we look at our sun, we are seeing what it looked like 8.5 minutes in the past because it takes that long for the light to reach us. So here, we're seeing the universe as it was about 10 billion years ago. And interestingly, that means we only have a little bit farther to go here because there is an edge to everything that we can see in the universe. And that edge is all around us now, this kind of blurry background you see here, this reddish orange background, that is the cosmic microwave background radiation, or the CMB. Now, this light is the residual radiation from the Big Bang, and it is the earliest light that we can see with our telescopes. If you had a radio telescope that could see in the microwave range of the electromagnetic light spectrum, you could see this everywhere you look in the sky. In fact, the first radio astronomers, they were pretty confused by this because they looked up into the sky with their telescopes and thought that they were getting interference everywhere they looked. But soon they realized that this is something out in space that they were actually seeing. And what we're seeing here is a few 100,000 years after the Big Bang would have happened. So you can kind of think of this as a baby picture of our universe. It's the first light that we can see. But since this is the edge of everything that we can see, that does mean we can't go any farther. And so we've reached the end of our journey today. And we're going to begin our descent back home to Earth. So let's get on flying. Now, if we were actually this far away in space and we were actually flying at the speed of light, getting home to Earth would take us about 13.7 billion years. But thankfully, we are in a planetarium, so it should just take about a minute. But there's one more thing I want to point out as we zoom back home. All of this that we have looked at today, all of these stars and the galaxies and the cosmic microwave background, that's not even everything that's in our universe. There is dark energy, a mysterious force that's causing space itself to accelerate as it expands. There's dark matter, a mysterious substance that doesn't seem to interact with light at all, but we see evidence of it in between and at the edge of galaxies especially. And we call these things dark energy and dark matter because we are not quite sure what they are yet. But we do know that they make up about 96% of our universe. So everything that we have looked at today, everything so far, that's only about 4% of everything that is out there. And sometimes knowing this makes me feel kind of tiny because we're just one little dot in a humongous universe. But then I do remember that even as a small dot, look at all that we have found so far, almost entirely just by looking through telescopes. So there is a whole lot more for us to discover out there and a whole lot more to learn about. And that's what makes this such a wonderful time in human history. We are able not just to learn these things now, but we can actually share them like this, mapping the cosmos in 3 dimensions. We're finally starting to unravel the true nature of the universe, but we're only starting to unravel it. And the rest, that's really going to be left up to the next generation of scientists back home on Earth. Now here we are approaching that 3rd planet from the sun now. The only place in all of this where we have found life so far. That's pretty incredible to think about after everything that we have just seen. Our tiny blue and green home is a pretty special place in the universe after all. So I'm going to drop you all off here. And that's going to conclude our journey together today. And I want to thank you all so much for joining me on this tour through the universe.